Okay. Good afternoon, everyone. I'm Zhou Dong from EMC Office of CTO and the EMC Lab channel. Thank you for the committee to give us this opportunity to show some research funding we did in the past few months. It's a great honor. We have been using Spark intensively in our security analytics project, as deep learning is the hottest topic in recent several years. We wonder if we can apply deep learning in our security analytics project. We have tried some deep learning on Spark framework and got some experience to share with everyone here. So today, our topic is, which is a deeper comparison of deep learning framework on Spark. Let's go through the outline. First of all, it's the motivation. Why do we want to conduct deep learning on Spark? Next, I will spend a little time to introduce the theoretical principle of deep learning on Spark. It will guarantee deep learning on Spark is feasible. And next, I will introduce how many participants in deep learning on Spark area and who are they. Following, I will give our evaluation criteria and the evaluation result. Finally, it's summary and the conclusion. Motivation. Let's see why industry want to integrate these two technologies together. For deep learning, most use cases are used in single machine. Obviously, single machine deep learning has limitation. One is low efficiency. You also have to train a complicated model in several hours to even several days, even though GPU is enabled. After limitation is a limited deep learning neural network model capability. It's hard to support billions of parameters for single machine. Most of deep learning work has focused on training relatively small models on a single machine. So we think this distributed deep learning is the right direction. Google just released the distributed version Tensorflow in April. The second motivation is there are several shortcomings for dedicated deep learning cluster. The first one is the massive data movement. Look at this picture borrowed from Cafe on Spark. And there are two clusters. One is deep learning cluster, and another is a Hadoop Spark cluster. Now we want to use deep learning cluster to analyze the data stored in a Spark cluster. We have to load the data from a Spark cluster into a deep learning cluster after training and the conclusion, and then send a huge model back to the Spark cluster. The massive data movement is high time consuming and network consuming. The second shortcoming is a high cluster maintenance cost. I think it's quite obvious. So based on the above reason, industry start to combine deep learning and Spark into an all-in-one solution. It could not only train complicated DNN model in a reasonable time, but also could let user use deep learning as same as use MNIST or GraphX without unnecessary data movement. It's a truly all-in-one solution for comprehensive end-to-end big data analytics. Now let me introduce the theoretical principle of distributed deep learning. Distributed deep learning is derived from paper of Jeff Dean in 2012, large-scale distributed deep networks. It introduced two kinds of parallelism, model parallelism and data parallelism. Model parallelism is very complicated. Look at the left picture. Model is split into several parts. Each worker only train one part of a model. The main problem is how to synchronize the model's different parts. It would be a very complicated process. Now, no deep learning on Spark framework has implemented model parallelism. The right figure is data parallelism. It's relatively easier. Model will be not split. Each worker will maintain a complete model. Now, all deep learning on Spark framework use all deep learning on Spark framework use data parallelism. So it's necessary to highlight the data parallelism. In data parallelism, model is replicated on each worker node across cluster. The training process only contains two repeating steps. The first step is to train each model replica with mini batch in Spark's executor. Mini batch is an iteration to train subset of data. The second step is to synchronize model parameters across cluster. The step is quite straightforward, but a specific implementation could be different in following three aspects. The first difference is how parameters are compiled. User can just average the parameter or do some complicated mathematical calculation. So sorry. Second difference is the synchronization extent. There is an implementation in Jeff Dean's paper. It's called a down power SJD, and its synchronization extent is weak, which means in its implementation, fetching parameters and updating parameter is asynchronized with the training process on a mini batch. The third difference is architecture of parameter server. Most implementation of distributed deep learning use the centralized parameter server. There is a dedicated parameter server. Another kind of architecture is peer-to-peer, the decentralized parameter server. In decentralized parameter server will be distributed on each worker node. After theoretical principle, let's look at all the participants in deep learning on Spark area. Here, I list most of our mainstream deep learning on Spark framework. AMPLab's SparkNet, Yahoo's Caffe on Spark, Ramo's Tensorflow on Spark, SkyMine's Deep Learning 4J, Baidu's Paddle, DeepDist, and H2O's Sparkling Water. Today, we will just focus on the top 4 frameworks as time limitation. Who are these participants, and how about their product? So now, let's start to look at this deep learning on Spark framework one by one and make the choice, which is deeper. Before giving evaluation result, I need to give our evaluation criteria at first. We will evaluate each framework from 5 aspects. The first aspect is ease of getting started. When you start to touch a technology, you certainly want to get started as soon as possible. There are 3 dimensions regarding determining how easily you can get started with this framework. The first one is documentation. Documentation here is any materials that can help users to learn frameworks, include paper, blog, presentation slides, videos, and so on. The second dimension is ease of installation. How installation automatic process will be. The third is whether it provides detailed example to help users quickly learn how to use same framework. The second aspect is ease of use. 2 dimensions are interface, model encapsulation extent. What programming language it uses is not an evaluation criteria. At least here, just want to help users to make choice. If it could support a multi-language, even SQL, it will be a big plus. Model encapsulation. When we are using MLE, we just need to select the right algorithm and configure the parameters. But for machine learning, we have to configure the here is a little bit trouble. We still need to select the algorithm such as CNN or RNN, but different from machine learning, we have to configure the network topology of a neural network. This is not a simple work like configure parameter. So if a framework could directly give a well-configured network topology or could use the model of Caffe or TensorFlow directly, we think it is a model extent. But not if a framework predefined layer API, we consider it's a layer extent. The lowest encapsulation extent is node. In node extent, we also have to define each node and then define each layer and then define the model. The third aspect is functionalities. The first dimension is a building model. It's similar with the supported algorithm of MLab. The second dimension is a parallelism, model parallelism or data parallelism. We have explained it in the theoretical principle. The fourth aspect is performance. We will use a data-side MNIST to do the benchmark, which all framework has implemented is as an example. The last aspect is the status quo. The first dimension is community vitality, how strong and how actively they are making contribution. The last dimension is enterprise support. It's the contribution from organization or just a personal project. Now let me introduce all frameworks one by one. The first one is SparkNet. It's released by AMPLab from 2015. SparkNet doesn't implement deep learning algorithm by itself, but just wrap the model or Caffe. Model of Caffe or TensorFlow. It uses a centralized parameter server, which run in run driver side. SGD synchronization extent is strong, which means the fetching and the updating parameter are running in same thread with the mini batch. There's a differentiating feature for SparkNet. Each worker runs a fixed tau of iteration on its subset of data. It could enhance the weights changing effect of each SGD, but costs more time. You also need to trade off here between training effects and time consuming. Let's fill out this table. Documentation. There is a paper to introduce how it implemented. There's no blog. All the installation guide and usage are on the README of GitHub, but the README is relatively simple. If you try to submit the job according to the given statement, it throws an out of memory exception. I ran it successfully after modify archive frame size and a driver memory. Installation. A user don't need to install, just need to build a jar file and copy source code to each node. There are some errors during building process. I suggest you disable test before building a jar file. Example, it has no too many examples, but have comments such as MNIST, interface, Java and Scala, NoSQL interface, model encapsulation, model and layer. At first, I look at the usage of model extended. A model here is to load the TensorFlow model into SparkNet and generate a disk structure named TensorFlow net for training use. Next, it's an example of layer. We can see that the SparkNet has predefined several layer APIs such as IDD layer, convolutional layer, and pooling layer. If you want to use the layer API, you have to fully understand the network topology of this algorithm and translate it into your source code. Building models. Or Caffe and TensorFlow model could be used in SparkNet. It will be wrapped into Caffe Solver or TensorFlow Net. This is a big advantage. But there is still problem need to be noticed. SparkNet now only supports TensorFlow version 0.7. I have tried TensorFlow 0.8 but failed. Parallelism, data parallelism. As mentioned before, all deep learning on Spark framework parallelism now data parallelism. Next is the performance. We use the MNIST as a benchmark. Look at this picture. Look at this table. I picked several points here. It can be seen that the relation between time and the iteration is linear. The accuracy is up to upper bound before 1,000 iterations. We will give a benchmark comparison chart later. Community vitality is easy to quantify. There is almost 400 start and 5 contributors. Obviously, the community is small, but I think it's still growing. Enterprise supported. There's no commercial version, and so far most of support are from AMPLab. Here are my score from a user and developer point of view. It's just for reference. The second framework is Deep Learning 4J, released by SkyMind from 2014. According to their introduction, it is an open source distributed deep learning project in Java and Scala. It is a generic deep learning framework and can run on Spark. The computation model of Deep Learning 4J is based on MapReduce, but it's an improved MapReduce, iterative reduce. It mitigates the disadvantages of MapReduce in the iterative computation. And it implements a strong SD synchronization. The parameter synchronization and the broadcast happen in reduced side. Let's fill out this table. Documentation. No paper. All materials are in official website. The document is comprehensive, detailed, but not so well organized. For non-expert of deep learning, it will incur confusion. Deep Learning 4J consists of many independent components, such as ND4J, ND4S, but the relationship between them are not very clear. It's a little bit confused for me to determine which component it must be. Actually, Deep Learning 4J introduced itself in its document as comprehensive but complex. Installation, enough to install, and it provides a pre-built version to run quickly. It's so convenient here. Example, there are only 3 examples here and specify CTH5. I didn't use CTH5. It could be run, but still have some problem. For example, it cannot be detect OpenBLAS. Even though I have installed it successfully, it affected the performance seriously. Interface, Java and Scala, and no SQL interface. Model encapsulation, layer. The API is very well defined. User use it like this. Define each each network layer structure and set parameters. Building model. It provides most of mainstream DNN model. Parallelism, data parallelism. Performance. Each apex finished when apex finished 15 times, the accuracy reached the upper bound 88.7% and costs more than 21,000 seconds. It's really low efficiency compared with others. I need to mention here the reason low efficiency may be because the OpenBIS cannot be detected. Community vitality very good. There are many contributors. Enterprise support. It has commercial version, and most of the contribution comes from SkyMine. And this is my score. The third framework is Coffee on Spark, released by Yahoo from this year. There were talk about Coffee on Spark given by Yahoo yesterday. So here I just give a simple introduction. According to their blog, they want to do this because they have a lot of business use deep learning, include Flickr and image search. And they don't want to build and maintain two clusters like this. So they want to integrate two into one, like this. The architecture of Coffee on Spark is peer-to-peer. No dedicated parameter server as shown in this figure. The parameter server is not in driver side, but is sharded by nodes in the cluster. Parameter synchronization between model is by TCP or RMDA. This picture gives an introduction of parameter synchronization process. There are 3 worker nodes. Each node holds 1 copy of parameters and is only responsible for updating and synchronizing their own paths to peers. The arrow direction indicates width propagation, and the reverse direction means send back the gradients. The synchronization extent, the HD synchronization extent is strong. There is a differentiating feature for Spark Online, Coffee on Spark. Sorry. They use the O-reduce of an MPI to synchronize parameters, and the parameter synchronization between nodes support InfiniBand. Let's continue to fill out this table. Documentation. There is a blog to introduce their project, but no detailed implementation. All the installation and usage are on the README of GitHub, and the README is relatively detailed. Installation is inconvenient, I have to say. User has to install all Cafe's dependencies such as HDF5, Boost, even OpenCV, which is an optional dependency. Example, OpenCV10 and MNIST interface, Scala and Python. Model encapsulation model. User just need to cite Cafe model's path and inconf, and then you can start training the model. The encapsulation is very good. Building model, all Cafe is supported. Parallelism, data parallelism. Performance, same as the SparkNet, the relation between time and iteration is linear. The accuracy is upper to upper bound between 1,000 and 2,000 iterations. Community vitality, it's not bad. It's between DL4j and SparkNet. Enterprise support, there's no commercial version, and it's supported by Yahoo. Here's my score. The last one is TensorFlow on Spark, released by Arimo from 2015. It's a data parallelism done power SGD implementation on Spark. It is strictly followed by a synchronized SGD in Jeff Dien's paper, and it uses a centralized parameter server and a weak SGD synchronization. Let's continue to fill out this table. Documentation. It's very simple, but I have a blog, presentation slides, and videos of Spark Summit East this year. Installation is easy. Users only need to install Tornado and TensorFlow. Example, Common example only have MNIST interface, Python, and NoSQL interface. Model encapsulation, model and layer. Because TensorFlow on Spark is based on TensorFlow, so it can be seamlessly integrated with TensorFlow's model. If the user is familiar with TensorFlow, you can also use the TensorFlow's API to generate a model. A built-in model. All TensorFlow supported model. Parallelism. Data parallelism. Performance. When Apex finished 15 times, the accuracy reached the upper bound 96.7% and cost more than 2,600 seconds. There is one thing need to be noticed. The relation between the time and the iteration has been already not linear. The scalability of this framework needs to be tested further. Community vitality. Its community is still in the early stage, I think. Enterprise support. It has a commercial version and supported by Arimo. Here's my score. Let's summarize the benchmark. Our test environment is 6 machine cluster, 1 master, and 5 slave. We set the executor memory to 20 gigabyte and set the training model batch size to 64. Look at this chart. We can see except DL4J, the accuracy of our other frameworks quickly reached to upper bound. And the accuracy is greater than 90%, except DL4J. The DL4J's performance is much worse than other framework, and the accuracy upper bound is below 19%. In this slide, let's remove DL4J. From this chart, we can see that different frameworks have different accuracy upper bound. For this 3 framework, Coffee on Spark's performance is best. It can reach the accuracy upper bound more quickly and have a higher upper bound. The second is TensorFlow on Spark. We can observe the isolation of accuracy from TensorFlow on Spark, which may be typical because of its asynchronous nature. Here we give a complete summary. We summarize all scores in one table. As can be seen, each framework has its good parts, but also has its shortcomings. Like I said before, it's just from a user and a developer point of view. And just for reference. Conclusion. From industry, there are a lot of things need to do. The first one is model parallelism. We all know it's difficult, but it should be done. The second is potential network congestion. As model is larger and larger, and the introduction of GPU, the data exchange between each node will dramatically increase. How to solve the potential network congestion is crucial for the future of a network or a framework. Last one is the development of each work. Frankly speaking, now the entire deep learning on Spark industry is in an early stage. There are a lot of things need to do to improve and perfect the framework. From our side, following our future evaluation work. For the first one is GPU-related work. We didn't do too many GPU-related work. The main reason is that Spark doesn't support GPU directly. If the time and resource are low, we will spend some effort on this. The second one is HDD synchronization. As mentioned before, different frameworks use different synchronization extent, but we still haven't made clear which is better. In the same way, we still don't know which architecture is better, centralized or peer-to-peer decentralized. The last one is scalability. About scalability, it's crucial for cluster scale out. We didn't do too much work here, but we have found some framework have problem in this area. So that's all we need to do in next phase. Okay, thank you.
Excellent. Questions? Please say your name and where you're coming from.
Hi, I'm Bertolt. So did your performance numbers include GPU or not?
No.
No GPU at all?
Yeah.
Because the examples were very small. I could have run them on a single node.
Yeah. Frankly speaking, we have no enough resource to test GPU.
Okay.
Yeah.
And for second question then is for Cafe on Net. You said it can
Cafe on Spark?
sorry, SparkNet. It can
SparkNet?
also use TensorFlow.
Yeah, you can load
Okay, so in
TensorFlow.
your experiments, numbers that you showed for Cafe on Net, sorry, for SparkNet,
Yeah.
what backend did it use? Did it use Cafe or did it use TensorFlow?
I'm sorry?
SparkNet.
SparkNet, can you repeat the
What engine did it use? Did it use Cafe or did it use TensorFlow?
engine? So you mean? It's a wrapper on top of. Yeah, it's a wrapper of Cafe or TensorFlow.
And the experimental numbers showed.
It's use a MNIST as the example.
No, the performance numbers.
Performance
Did it run on Cafe or did it run on TensorFlow?
TensorFlow. Yeah.
So why were the numbers so different comparing SparkNet on TensorFlow compared with just TensorFlow?
I can answer this question because I think there's a different implementation of different framework. Maybe the I think the synchronization the parameter. I think the different implementation in the synchronize the parameter and broadcast the parameter. This maybe because this.
Okay, thank you.
I wonder what's the easiness of model persistence after you train those model and such that in future you can easily put them into production to use your model. Have you evaluated them?
I'm sorry. Can you speak slowly?
Oh yeah. So how easy it is to persist your model, such that you can use your already trained model in future for your production?
I can see the our criteria. Sorry. If the model encapsulation is a model layer, I think it can it can load the TensorFlow's model or the Cafe's model directly into their framework. It can use it directly. Well,
You have a Java file or something? If you are using Java, you can have a Java file?
yeah.
Okay.
Yes.
Can you comment on how well these frameworks deal with sparse data?
Spark data.
Like I know native Cafe cannot handle like create models with sparse data, but
So can you
oh sorry. So like can you comment on the fact that how well do these frameworks deal with sparse data?
Spark data?
Sparse. Like,
I'm sorry. Spark data? What's
sparse data.
the sparse data? 什么东西? Oh, I'm sorry. I'm not so clear with this algorithm related to
Okay.
the question. I'm sorry.
Excellent. Let's give him a hand.
Okay, thank you.